So let us see what we mean by an inverse Laplace transform. First of all, when we take the Laplace transform, we're transforming this function f of t into the Laplace domain, which we call f of s. Now the inverse Laplace transform is denoted as follows, where we want to go from the Laplace domain into the time domain. So here we're taking the inverse Laplace transform of f of s, and now we're get f of t. So here's an example. The Laplace transform of 1 is just 1 over s. The inverse Laplace transform of 1 over s is equal to 1, or a constant. Laplace transform of a ramp t is equal to 1 over s squared. The inverse Laplace transform of 1 over s squared is equal to t. And then finally, we have the Laplace transform of this exponential e to the minus 3t, which is equal to 1 over s plus 3. And the inverse Laplace transform of a 1 over s plus 3 is simply e to the minus 3t. So the inverse Laplace transform just goes the other way, where we can go from the Laplace domain to the time domain. Now let's look at some typical inverse Laplace transforms, very similar to what we did earlier with the Laplace transforms. The inverse Laplace transform of 1 over s is equal to 1. The inverse Laplace transform of 1 over s minus a is equal to e to the minus at, or simply exponential. Here the inverse Laplace transform of n factorial divided by s n plus 1 is equal to t to the n, where n is equal to 1, 2, and 3. And we note that from the ramp it's t squared, so it's just 1 over s squared. Here we have the inverse Laplace transform of k divided by s squared plus k squared, and that's equal to sine of kt. Here the inverse Laplace transform of s divided by s squared plus k squared is equal to cosine of kt. The inverse Laplace transform of k divided by s squared minus k squared is just the hyperbolic sine kt. And the inverse Laplace transform of s divided by s squared minus k squared is equal to the hyperbolic cosine kt. And that's some of the typical inverse Laplace transforms. Now when you evaluate these inverse transform, it often happens that the function of s under consideration does not match exactly to any of these forms of a given Laplace transform f of s. So it may be necessary to tweak that function, fix it up of function of f of s by multiplying and dividing it by an appropriate constant. So let's do some examples on applying the inverse Laplace transform. Let's say we want to find the Laplace transform for the inverse Laplace transform for the following function, where we have 1 over s to the 5. Okay, so here it's still not in the shape, because if we recall, to match one of our inverse Laplace transforms, we'll just take this function and multiply it by 1 over 4 factorial times 4 factorial to match one of our inverse transform functions, as shown right here in this one right here. Okay, so that should be equal t to the 4th, but 4 factorial is simply 24, so it's just t to the 4th over 1/24th, and that's our inverse Laplace transform associated with 1 over s plus 5. Okay, let's do another example. Let's say we want to find the inverse Laplace transform of 1 over s squared plus 7. Let's just look at the form from the previous slide, which sort of matches what we have here. And we see that the sine kt is a form of the function we just looked at, but except it has a k squared in the denominator here and a k at the numerator. So we'll put that in that form so we can find the inverse Laplace transform associated with this function. So in other words, we'll take this function 1 over s squared plus 7 and we'll put a square root of 7 on top and a s squared plus square root of 7 squared, because square root of 7 squared is just simply 7. However, since we multiplied the numerator so we can get it in our form that we just saw of square root of 7, we need to divide by the square root of 7. Now that we have it in this form, it's just a scalar multiple of 1 over square root of 7 times the sine, and our k in this case is square root of 7 t. So that's how you modify this function to fit it to one of our inverse Laplace transforms pairs in this table. We also should note that the inverse Laplace transform is a linear transform. Again, what we mean by that is that if I have a linear combination of alpha f of s plus beta g of s, so it's a linear combination of Laplace transforms, then we have alpha f of t plus beta g of t. This is what we mean by a linear transform. We can do an example now. So let's apply this linear transform associated with the inverse Laplace transform with this example. We can rewrite this as two separate inverse Laplace transform as minus 2s over s squared plus 4 plus the inverse Laplace of 6 divided by s squared plus 4. Now we can rewrite this expression again with this modification of constants so we can match what's in our previous table of inverse Laplace transforms, such that we'll factor out the minus 2, and this is just s over s squared plus 2 squared, and then this will be just 6 divided by 2, since we want to put a 2 in the numerator here, s squared plus 4, and then we take the inverse Laplace transform and we have this relationship. Okay, so we recognize that if you look at the tables, this is just minus 2 cosine of 2t plus 3 sine of 2t. Again, we took this 2 and this 2. 2 divided by 2 is simply 1, so we modified this function such that it fits the form in our inverse Laplace transform table. And now that we recognize that this is just a sine function, well, we can rewrite this 4 as 2 squared, then we can see that this is 6 divided by 2 is 3, and this function has the form of sine 2t.